So we're happy to have first Wang-Yu Xiao from University of Washington, and he's going to tell us about axion dark matter in the sky. Please, Wang-Yu.
Okay, thanks. It's nice to be here. And today I'm going to tell you about axion dark matter in the sky. And the storyline is like this. First, I will motivate axion as an interesting dark matter candidate. Then we'll tell you a story about the substructure formation from axion perturbations. Then finally, I will discuss the detectability of axion minihalos. So first, it's about the theoretical motivation of the axion dark matter. So axion was originally proposed to solve the so-called strong CP problem, namely why the CP symmetry is conserved in strong interaction, and there is no reason for that. So we have a good measure for that CP symmetry, which is the neutron electric dipole moment. So if this neutron electric dipole moment is 0, then CP is exact in strong interaction. If it's non-zero, then it's violated, and we can measure it. And now we can think about the electric dipole moment just classically. We have three quarks, two down quark and one up quark. So just remind you, up quark has a charge plus 2/3, down quark has a charge minus 1/3. And then naturally you would expect there will be some angle between these two lines, some theta angle. Therefore, you can do your classical calculation. You sum over the charge times position. You will find if this theta angle is non-zero, then you naturally have some non-zero electric dipole moment. However, from the measurement of the neutron electric dipole moment, we know this dipole moment is extremely small, and that gives you an extremely small theta angle, which is smaller than 10⁻10. So this small number is really mysterious. The isotropic solution is not likely, unlike other fine-tuning problems, because just imagine this theta number is still small, but not that small, like 10⁻3. Our nuclear physics will be still pretty much the same. You will still have Big Bang nucleosynthesis, galaxy formation, star formation, you have everything. Our human being can still be alive. So it's not likely to have an isotropic solution. And axion is a really nice solution to it, because we can imagine maybe this theta angle is not a fixed value, and it's a dynamic angle, and theta equal to 0, it's simply the ground state. So of course, at a quantum level, we don't have this geometric angle anymore. We shouldn't think about that. But we still have this theta parameter in field space, and it's still the measure for your CP violation. So we can promote this parameter to a dynamical field, and you will have some potential arise from strong direction, which is given by this cosine potential. So if you start from some non-zero theta value, it will just naturally relax to the ground state, which will eventually gives you theta equal to 0, which will give you an exact CP symmetry in strong interaction. And this is done by Postinflation in 1977. So it has been around for a while, for many years. And also this solution, the axion solution, can naturally give you dark matter as well, because you have potential turned on by strong interaction. And before QCD phase transition, before strong interaction was turned on, this potential was pretty much flat. And then it was turned on at the temperature about 200 MeV, which gives you some cosine potential. Therefore, you have some non-zero vacuum energy. You get some non-zero vacuum energy from this process, and then that non-zero vacuum energy can convert to matter density, which gives you the dark matter relic abundance. So this is called the vacuum misalignment mechanism. And to produce the correct dark matter relic abundance, we know what axion mass you should have. So you don't have much freedom on your parameter space. This axion mass will be about 10⁻⁵ eV. And therefore, it's a well-motivated dark matter candidate. You know what is the mass, you know roughly, and it's really, you don't have much freedom. You can just look for it. Okay, now I will tell you the story of substructure formation, and we call the initial substructure axion mini clusters. And it's again from the mechanism to produce dark matter. We have uncorrelated field values. So I've shown you a plot that we turn on the potential, we convert vacuum energy to dark matter, and those field values will be uncorrelated at different horizon patches. Therefore, you would have order one white noise matter density fluctuations because you convert that vacuum energy to matter density. Therefore, and this is a plot to show you the inhomogeneity on the matter density. Therefore, you would form mini clusters, very dense objects called axion mini clusters at matter radiation equality. And that would be very small substructures. And the size of the mini clusters is actually given by the horizon size. So if we consider the QCD axion, which is the axion that solves the strong CP problem, the characteristic mass is really just the mass contained within the horizon at the moment roughly when your QCD was turned on. Therefore, it's given by this volume times your conmoving dark matter density, which is about the benchmark is about 10⁻⁻10 solar mass. So they will evolve and merge. We call them axion mini halos at later times. And the inhomogeneity can be well described by a white noise pulse spectrum because the matter density, as emphasized, is randomly distributed and uncorrelated in different horizon patches. Okay, so that's the axion mini clusters. We can naturally have a few questions for the axion mini clusters. Are they detectable? You may think not, because I gave you the characteristic mass, which is as small as 10⁻⁻10. So it's really the smallest objects you might imagine in our universe. And how do they evolve with time? This should be addressed using embodied simulations. And also, third question, are there still axion particles that remain unbound? This would be important for direct detection. So I will use embodied simulations to directly study the detectability, the evolution of those axion substructures. Okay, detectability of those mini halos. I've talked about theoretical motivation of this project, of this axion, but really the real motivation for this project are those new ideas of detecting small-scale structures. So we have, and otherwise this project won't be useful. People won't care about it if there's no way to detect them. So it was really recently that people have ideas of seeing those small-scale structures. We have pulsar timing arrays, which could be probed in future SKA, and this would be sensitive to substructure masses from 10⁻⁻12 to about 100 solar mass. And we also have lensing in highly magnified stars, which could be seen in JWST. Excitingly, will be launched next month. And they will be sensitive to a similar mass range. So those small substructures are really detectable. And now is really the time to study the formation and evolution from interesting physics. And then we can say if we do study, we found a lot of formation of those substructures from certain physics like axion physics. That would be really interesting for future observations. And here is I will be using embodied simulations, and here is a simulation setup for this axion mini halos. I will initialize the particles with the white noise pulse spectrum and run it with the MP gadget. Before I move forward, I would like to compare the white noise pulse spectrum to the standard adiabatic pulse spectrum. So the adiabatic pulse spectrum is here. I'm plotting delta K at y-axis is really K cubed times pk. So this is your standard adiabatic. And this spike here is your white noise. This is because for white noise Paul spectrum, pk is about a constant. Therefore, this will be simply proportional to K cubed. And for such power, it's always going to dominate the high K powers. Therefore, in this regime, it's always going to be dominated by the white noise, and the substructure formation will be dominated by white noise. Therefore, for really small scales, you don't necessarily care about adiabatic. You can simply study the structure formation from white noise only power, and then probably that we will glue things together using analytic formula. So that's the reason we care about we run small scale simulation, we use white noise Paul spectra only. And the box of our simulation is 50 parsec, and the particle number is 1024 cubed. And we run this simulation from radiation error, a redshift of 30,000, to redshift 19. So this is pretty early universe. However, this redshift 19 is still the lowest redshift so far in the literature of simulating Axion minihalos. And I will show you later why a redshift of 19 would be sufficient to determine the detectability. And also just remark, this is a scale-free simulation because we only run simulation for this white noise power. It's scale invariant. This could be rescaled to arbitrary masses. So even though we are particularly interested in Axion, if you're interested in other mass ranges, you can still use our results.
Sorry, but for scale invariant simulations, don't you also need to be in the matter era?
Yeah, that's true. Okay, good. Yes, you need to be in the matter-dominated era, but because this is isocurvature fluctuation, the physics, the evolution in radiation error is more like trivial. So the homogeneity will not grow because this is isocurvature. But even though we start from radiation, yeah. So the assumption is that from this radiation to the matter radiation equality, they won't form interesting structures, and the homogeneity will not grow significantly, or it's like frozen before matter radiation equality.
So then why do you start so early?
Yeah, that's a good question. We think it's going to be more accurate to start it early, and also it's not very expensive to run it early because the evolution is just trivial. So it's not numerically expensive. We want to see if there's anything going on, but the result is that there's nothing going on. And also another reason that we started early is because there are a lot of groups who have been running simulations for really early evolution of Axion field, and they run simulation from symmetry breaking scale to perhaps QCD phase transition. So they run their simulation at really early times. So we are moving this forward and to connect this with real life observers. So we started early just to get closer to the early universe simulation. Does that answer your question? Okay.
So principle, if you would start at z equals 3000, you would get the same result.
Yes, that's right. Okay, now I can show you the result of the mass function. So the data points as a mass function from our simulation data, and we also used a tweaked Chateauman to fit the mass function at different redshifts. And you can see it doesn't work really well at low mass end, but actually we run another simulation using a Paul spectrum without a cutoff, and it agrees better. So this is simply to confirm that this disagreement at a low mass end is due to some physical cutoff, but not numerical artifacts. And also, if we integrate over the mass function, you will find that the collapse fraction is about 75% at the redshift 19. So a lot of dark matter has collapse to those substructures because you had order one fluctuation on the white noise power. So this is a lot, and this would, I will show you later, this will be detectable.
Sorry, how big was your box?
The box is 50%.
But what is the nonlinear scale at redshift 19?
Okay, good question. And it's still linear at redshift 19.
50 parsec linear redshift 19.
Yes, 50% is still linear at redshift 19. And actually, I have a slide to show you later. Okay, so this Twix-Chateau works amazingly well, and that allows us to extrapolate our result to even lower redshifts, because you can see it agrees well with the simulation data at all kinds of different redshifts. And however, we have to make assumption when we do that extrapolation. Once minihalos fall into large-scale structures, they stop merging. And this is motivated by the high virial velocity of those large structures. So if you simply have two minihalos in large structure and they encounter with each other, because the velocity is so high, it's hard for them to stop each other and merge. Therefore, we assume at the moment they fall into large-scale structures, their population is frozen and they stop the evolution. This model could be inaccurate, and we leave it for future studies. And because
when you said that you were linear at 50 parsec, you meant for your white noise power spectrum?
I mean for the whole box. I mean the whole box has an collapse.
But because you only have this.
Yes. I mean
you
for
have
the
the cosmological adiabatic fluctuations. So in reality, somewhere much before redshift 19, the adiabatic fluctuations start to dominate in your.
Yes.
And you are not putting that.
Yeah, I mean, I'm trying to include that for this.
That's
for the next slide. Yes, exactly. Okay, thanks for pointing that out. As I said, we have a small box simulation, and this small box simulation doesn't know anything about the adiabatic fluctuation, and this mass function cannot be trusted anymore once large-scale structures start to form, which is happening around redshift 20. So you have to think about a way to include both, and we compute the so-called current mass function, including those incorporated into massive CDM halos, which is given by this protocol. And the story is you have mini halos, you have substructures from those white noise power, and because they are so small, they will eventually fall into larger structures formed from adiabatic, and then you assume, and then you have really good analytic description for the adiabatic, the structures formed from adiabatic powers, and then you can compute the mass function of those substructures at any given redshift, and assuming at the moment they fall into the large structures, they stop evolution, and you just compute every redshift the population of those white noise mini halos, and then you can integrate over the whole redshift, you get the total mass function, and then you extrapolate all the way to redshift 0, and that would be our protocol.
So the large scale structure is dominated by what? By what type of dark matter? By axions?
Okay, that's a good question. So we are still assuming all of the dark matter is axion, but axion has really interesting white noise pulse spectrum at small scales, but this is assuming at large scales it's still reproducing the adiabatic power which comes from inflation. So it's still axion, but axion at really large scale, and it doesn't care about what kind of dark matter you would have. It's simply coming from the inflation.
So how does this mini halos go into the small scale to the large scale? How are they related or connected?
So maybe we go even back to this plot. So this is a white noise pulse spectrum, and this is your adiabatic. So if you go from small scale to large scale, we simply study them separately. And for now, we are focusing on this end. And analytically, we will extrapolate this end to that end. We are assuming structures form separately from both on both limit, and then we glue things together. We assume those small mini halos will fall into large structures, and then you simply study that population. And then you assume, okay, you have standard structures born from adiabatic, and you have some structures from white noise at small scales, and then you study the falling process of mini halos onto large scales, and then you get the total population.
So these are assumptions. That's not comes from fundamental Axion dark matter distribution.
Exactly. So that's the current assumption of this project, and this could be accurate. So really, you have to model this process very accurately, and we leave that for future study.
Okay.
Does that answer your question?
Yes. Yes. Thank you.
Thanks. Okay. Yeah, this is really complicated. Maybe I should move forward. So besides the mass function, we also care about the density profiles, which will be also crucial for observations like lensing. So the conclusion is that NFW is a really good description, and I'm showing you the simulation results and the NFW fits. So we also have a really good analytic prediction for the mass concentration relation. And surprisingly, this also agrees well with our simulation results after you calibrate it with a prefactor. So the purple solid curve is simply given by this mass concentration relation. And you can see it largely agrees well with the simulation results. There's some anomalies at high mass end, and this high mass end anomaly is actually corresponding to the substructure of substructures in Axion mini halos. And the dashed curve is simply showing you what will happen if the concentration is a factor of 2 smaller. So to confirm that, to convince you that the anomalies here are because of the substructures, I'm plotting individual halos here. So those are individual halos, and they all have mass 10 to the minus 7. So you can see here, this is redshift 49, 32, 24, and 19. So you can see at high redshift, this mass will be at the high mass end. There will be some substructures, but they're not two separate mini halos. They are one single bound object. It's a single Axion mini halo, and they have some substructure. And that's exactly the reason you're seeing this anomaly, because at the center you have some substructures. You would expect this density profile would be flatter than you would expect from a naive NFW. So NFW is overall a good description for the density profiles, and we have a good prediction on the mass concentration relation. And here we can talk about observations. So in conclusion, microlensing in our model is not working well because the halos are not concentrated enough. However, pulsar timing arrays can detect Axion mini halos in the future, and lensing with highly magnified stars will also be able to detect those substructures in the future. So here is the mass function. I'm showing you the mass function. You can see I have the same shape but different characteristic mass. This is shifting simply because I'm choosing different particle mass on axions. And the bins here are corresponding to the required abundance you would need to see those structures in PTAs. And this dash curve is simply the required abundance for you to have lensing with highly magnified stars. So in conclusion, the population of Axion mini halos will be detectable in future observations of pulsar timing arrays and lensing with highly magnified stars.
Do these get disrupted by a baryonic process?
Okay, that's a really good question. So the question is that will they be disrupted for baryonic process like the stellar disk? we can talk this offline. This is the ongoing project, and it's complicated. It depends on the environment you're talking about. For example, for pulsar-timing arrays, you're talking about our Milky Way galaxy, and you have our stellar disk, and it's gonna disrupt. I can give you a number, roughly 50%. But for dancing with highly magnified stars, is in galaxy clusters, the disruption will be less significant. So you care about it less. But this is the ongoing project. So thanks for this question. And also, sorry.
How how would neutrinos, since we know that they exist and have mass, how would they affect it, since we are talking about these tiny halos?
Because you have some small mass object, and then they will affect the time of arrival through gravitational effects such as Shapiro time delay. So even though the time is the mass is so small, but because you can measure the time of arrival PTA so accurately, you will still be sensitive to such kind of gravitational perturbation. Does that answer your question?
But when the neutrinos cut off the low mass function at that point?
Oh, you mean you're talking about neutrino free streaming effect?
Yes.
Okay, great. Because this is totally decoupled from neutrino sector. So this is Axion, and you have and then you will care about the free streaming effect of Axion itself. And the Axion physics is interesting because it's generated from the so-called vacuum misalignment mechanism. So we convert that vacuum energy to dark matter density. Therefore, initially those dark matter particles will be really cold, even colder than the CDF. So the velocity dispersion is really negligible, and it will not wash out your small scale structures. Does that answer your question?
Okay, good. Thank you.
Yeah. So let me see if I have time. Maybe I should skip this. And so it's just, we talk about vacuum misalignment mechanism, but there could be also physical mechanism that introduce some uncertainties. But this is numerical uncertainty. It's simply because you have some topological defects, and it's really hard to simulate those topological defects. So there will be some uncertainties. People are still working hard on this to accurately predict what is the Axion mass to reproduce the related abundance, the dark matter related abundance. And I will skip this, and I would like to compare my simulation to other simulations in the literature. So there have been other simulations in Axion minihalos, for example, this redundance collaboration, and they using a simulation box size which is about 1 parsec, even smaller than my simulation, my simulation box. And their whole box will collapse, will be nonlinear at ratio 99, and they cannot contain the largest mini-halo. So they don't have that statistics for the majority of the Axion mini-halo. And our box is 50 parsec. It's still linear at ratio 19 if we are talking about white noise power spectrum. And then we have enough mass to contain the largest mini-halo. And our initial condition, as I emphasized, is white noise power spectrum. And for other works, they simulate the early universe evolution. They have an exact prediction for the power spectrum. And the white noise is simply the asymptotic behavior at the lower k. By lower k, I really mean it's still high k compared to other adiabatic fluctuations. But lower k is simply it's just above the horizon patch when you initially turn on the potential. So the question is white noise power spectrum good enough? Short answer is yes, because if you look at the power spectrum here, the difference of a different power spectrum will show up at the low mass end, and the high k powers will enter here. It will have an effect here, but the majority of the mass of mini halos will be at this end. And this is really described by the asymptotic behavior of your power spectrum, and white noise is a really good description if you care about observers like PTAs and the micronebulas with highly magnified stars. Therefore, we don't necessarily care about the detailed Paul spectrum at extremely high K, but white noise will be a really good description, and we can make very robust prediction for the observations, for future observations. So the conclusion is that we have enhanced small scale structures. About 75% of the dark matter will be in those substructures. And we have predicted the current mini-halo mass function for the first time with embodied simulations. And those substructures will be detectable in the future, even though they are as small as 10 to the minus 7. So that would be my talk today. Thanks.
Question?
Yep.
Yeah.
Your QCD model gives you a more or less specific axion mass.
Yes.
Now, when you vary the axion mass over several orders of magnitude, is that allowed by the QCD model, or are you just basically assuming it's another particle?
Okay, that's a really good question. And it's actually related to this uncertainty I was talking about. So people, if in this post-inflationary scenario, when your symmetry breaking is after inflation, you can form topological defects like axion strings. And axion strings can also produce axions, which means you have more axions from the decay of topological defects. And it's simply that people don't know how many axions you will produce from this process. And people have different results. They are running simulations for the string evolution, for the axion produced from this process, and different groups have different results. They don't agree with each other. So they have a mass range for that, and they have different predictions. But because my simulation is scale invariant, it's really easy for me to rescale my results to different masses. So I'm not leaning toward any group. I'm simply saying, okay, maybe you have different prediction, and I'm showing you they could all be detectable because I can rescale my mass to different masses.
Is the apart from the mass differences, does the QCD axion have the same physical properties as one produced by topological defects?
Yes. So different QCD axion mass will give you different dark matter related abundance, and then you have some extra contribution from the topological defect, and that will still be axions. So they have some uncertainties, and then in principle you could have different masses to reproduce the correct related abundance, and then I'm including that uncertainty and showing you different mass could still give you the same behavior. It's just that the characteristic mass, the peak mass of the structure of the object will be slightly different. So that's why I included this answer. Does that answer your question?
Yeah, more or less. It's a little confusing to me why a particle produced from a topological defect should be considered the same particle as one in your QCD model to make the dipole moment 0.
Oh, okay. That's maybe you can discuss this
in the
offline.
interest of time, we
Yeah,
can-
okay, that's fine.
because you will be around for
Yeah, I'll be
week,
around
so-
for the whole week.
so,
Yeah, I'm off campus.
oh, okay.
Anyway, it's okay.
Yes, we
Zoom,
can have
we can
Zoom
set on
meeting.
Zoom, yes.
Yeah,
So I think it will be possible to do that. So let's thank Ungyu again for the very nice talk. And let's go to Marco.
Let me share the screen. Do you see my screen?
Yes. So great, we have Marco Raveri from UPenn. Perfect, yes, we see everything. And he's going to tell us about learning the energy properties from cosmological surveys. Please.
Okay, guys, do you hear me? I'm Marco, nice to meet you. I want to tell you about my efforts in trying to mine out of cosmological data dark energy properties. And okay, and the starting point for this is basically our standard cosmological model, where we have a phase of accelerated expansion during inflation, then nucleosynthesis of chemical elements, hydrogen recombination, and then we go to a phase of the universe that's dominated by dark matter and dark energy. And precisely these two ingredients.
What was this drawing? Sorry.
This one?
Yes.
This is Planck. So this is all Planck.
Like artistic.
Yeah.
Wait.
I
never saw it actually. He's a cosmologist.
Yep. So, and precisely dark matter and dark energy are, the two cornerstones of the standard cosmological model, and are basically the target of the next generation of cosmological surveys that should measure their properties. And I've worked a lot in, trying to understand how we can make the best possible use of data from these surveys, trying to get, to the bottom of and potentially measure either dark energy or dark matter properties. And I'm going to show you a couple of examples today of what I think is the most powerful technique that we can use when doing it, which is model learning. And that's completely different from what we usually would do, which is model testing. Right? When we test a model, we basically just pick a model and compare it to the data. And for this process to succeed, we either need to be right, so we have to guess the right model that describes our universe, or we need to be lucky and find it by chance. And I've done that exercise many, many times in the past, and I was not lucky nor right. So I had to come up with something better. And that's the spirit behind model learning. And I'll show you two exercises, one more phenomenological and one more related to the physical properties of dark energy. So we start with the phenomenological exercise, where basically we want to be as vague as possible, as general as possible. So we just take the control equations of our physical system, in this case FW equations, and we break them. Right? In the standard cosmological model, we have lambda, which is a cosmological constant. Its energy density is constant. An empty glass today is empty tomorrow. And we break this by adding a time dependence in extended models. And we do the same thing when it comes to the clustering and lensing of large-scale structures, where we basically take the Poisson equation, the equation controlling light deflection, and again, we break them. And in both cases, we add, other unknown functions of time. And you can think of these two functions, mu and sigma, here as, gravitational constant for matter and gravitational constant for light that, in general could be different. And then the problem is that we are left with, unknown functions of time. And that's where, model learning differs really from model testing, because we don't really want to fix these functions, a priori based on some models that we have. We want to learn them from the data.
But are these supposed to be because you're including some additional forms of matter, or are they supposed to have you broken GR?
So in this case, at the most phenomenological level, the thing you're trying to do is just break the equations that you have in the most general way. So these are just, you have two equations, they relate to different quantities, and now they're basically free.
But this might not be a consistent.
Absolutely,
procedure.
absolutely. We'll see later when we start including, reasoning of consistency of models. That's the physical exercise. The idea of the phenomenological exercise is to be as vague as possible, because vagueness means that you are able to detect things that might be related to dark matter or dark energy, and they won't necessarily look the same, or you are more prone to detect something that's not expected. So functions of time, free functions of time, that's the problem that we are after. And if you think about that naively, there's basically no solution, right? A function of time is infinite degrees of freedom, and we always are going to have finite data sets. But fortunately enough, Gaussian processes literature in particular, and machine learning literature, teaches us that while the space of all functions is infinite dimensional, the space of bandwidth limited functions isn't. So we can try to reconstruct these functions of time by imposing priors on their time dependencies and how smoothly these should vary. And that's precisely what we have done. And we've done it in two different ways. In one way, we haven't taken any, any prior correlation. In the second way that I'll show you, we have taken, smoothness priors on the space of these functions that are calculated from, scalar tensor theories, from a whole, training set of these models that we have generated in the past. And as you can see here, for example, in scalar tensor theories, this plot on the right, not surprisingly, the gravitational constant for matter is highly correlated with the gravitational constant for light, and in particular, they're positively correlated, so that if you boost one, you also boost the other. While there's not much correlation with the background expansion history. And after we impose these, these correlation, these smoothness priors, we can reconstruct these free functions of time from data, and that's what you see here. Without a theory prior, with a theory prior on the right-hand side. And when we look at these plots, you can see all sorts of different features. These are directly coming from the data. In this case, in particular, the data we use is basically all cosmology, CMB, BAOs, supernovae, are all up to the clustering and lensing of galaxies from the dark energy survey. And some features here are statistically significant. You see, for example, that in the no prior case, there's significant fluctuations in the energy density of dark energy in this case, while those are too fast to be described by scalar tensor theories. So they are washed out once we use the prior. And the other two, statistically significant results that you see from this plot are basically deviations from one for sigma and mu from the two gravitational constants at later times. And we'll see in just a little bit how these play out in, with the discussion on cosmological tensions. Now, if you think about these figures, these are actually just projections of very high dimensional parameter spaces. So you need to be a little bit careful with the statistics to extract what you've just learned from these plots. And here you see, how the deviation from GR decomposes into the spectrum of modes and how different modes contribute to deviations from GR. And as you can see, for example, when we include large-scale structure surveys, all the modes that concern the two gravitational constants do increase in statistical significance of detection from GR.
Sorry, I don't think. What are these modes?
So these are the signal-to-noise ratio modes of deviations from GR.
Signal-to-noise ratio modes of these functions.
Yes, exactly.
So there are three of them. That's why there are three panels. So what is it?
Yes, we can't hear you.
Exactly. Who is talking? I couldn't hear.
I just learned from campus. We can't really hear Matthias when he's speaking, so maybe just speak up.
Okay, sorry. Yeah, I was just asking what was being plotted in the plot.
Yeah.
What were the modes?
So these are the PCA modes of the three functions, and then the signal-to-noise ratio with respect to GR of all the modes. And I think it's interesting to see that basically, they jump up in signal-to-noise ratio once you include large-scale structure surveys, basically because of the ES data. And then one other interesting thing that I read from this plot is the number of them. There's a number of constrained modes, which is much, much higher than what we usually use when we do model tests of simple parameterizations. That's basically telling us, that we have 15 data constrained modes, 15 properties of the energy and gravitation that, we know. And there's also a couple of fun facts.
How is this possible? How is this even possible? Sorry, the DES, yeah, how is it possible? Aren't these modes more and more oscillatory? What are they?
Yes, some of them are more and more oscillatory.
How is it possible that this DES gets 15 numbers? Yeah. How is it? Do you have a gut feeling? How is this even possible?
Yes, I should have put in backup slide. So you can plot these modes, and basically those are, they correspond to the band powers of the lensing power spectrum at different scales. So it's basically, the S is measuring about, not all of them are significant here. The S is measuring about 8 in sigma, right? And those are basically power spectrum at different scales. Because these time dependencies, right, they would change how the different scales in the DS measurements project, right? And then you basically have a different view of the, the data range.
What do you do with other cosmological parameters here? You also vary them.
Yeah, everything is varied. All the nuisance parameters are varied and all biases are varied. But constrained doesn't mean constrained very well. So one of the things we can read from this plot, is that constraints on the gravitational constant for large-scale structures is like constrained at the 50% level, 100% level. So framing in all the constraint discussion in this framework means that we do have constraints, but the constraints are really order 10-20% across.
You're saying in order to describe this curve, in principle, I can extract 15 parameters from just these curves.
Okay, and another thing you can extract, which is much funnier, is that you can compute signal to noise ratio instead of with respect to GR, with respect to 0. So, we were able to detect the clustering of matter, right? Mu equal to 0 would mean that matter won't cluster. And that's detected at 20 sigma from all cosmology alone. And, light deflection alone is detected at 32 sigmas. And that's actually slightly lower than I would have expected before doing this exercise. Okay, and the statistically significant features that we have seen in the previous plot are tied to the tensions that we are having in our standard cosmological model. And you see them, summarized in this plot where you see the CMB lambda CDM parameter posterior, and then the two parameters quantifying the expansion rate of the universe and the clustering of cosmological structures. And you can see that, they're into different places at different statistical significance. And now we can ask what's this picture and whether, these reconstructions of dark energy properties tried to explain these tensions. And the answer is sweet and sour in a sense, because as you can see from these plots, the tension over the growth of structure is totally real. You can just shift and go on target because these models have a handle to do that. That's sigma. On the other hand, the Hubble constant tension is only halfway real, and that's the sour part. And it's basically impossible to go fully on target. Sorry?
For shoes, not TIGG.
Yeah. I mean, if it was 70, it won't be this bad. But basically, the statement is that, this goes up, these type of models can go up to 70. And the reason is the following, really. That, you can plot out distances calibrated by shoes and calibrated by the CMB and BAOs calibrated by the CMB on the same plot. And the two things are just in different places. You get to draw a line in this plot and you can't be in two different places at the same time. And as you can see, the reconstruction tries, starts from the calibration of CMB and tries to lower and go down to meet shoes. But there's only that much wiggle room in the BAO data. And as you can see, the no-theory prior reconstruction that can oscillate faster than the other, gets a little extra edge, at the end, when basically BAO measurements are done. And so that's the trick that these
Why
reconstructions.
doesn't it try to go all the way down if you have free functions of time?
Because you still have, some correlation between different ratios. So you would say, go down like this, but that's a mode that's discouraged by the correlation prior.
But this is in the case of that you put these priors. Or did you always put it on
there is always some sense of prior that would prevent basically from
You're just saying it's just too fast. You can point. You
Yes.
never allowed such a fast.
exactly. And
Is
also
this-
because this is log redshift, right? This is nicely linearly spaced, but this is log redshift, so that's very tiny. It's
Yeah,
very tiny.
but if you were to plot in physical time, maybe there is more room or something. Like, is there some assumption that you made about smoothness in what x-axis and fast varying in what x-axis? Why can log z be the,
Oh,
for
well, actually,
example,
so
why can,
there's also another.
oh, I guess nobody hears me, sorry. You can repeat the question.
Yeah. So Matthias was asking why, the blue line, why can't it go deep, right? And just go on target where you get rid of the VAOs. So there's a little bit of correlation prior in the discussion, but actually one of the reasons is that both curves have to respect the shape of the supernovae signals, right? So in addition to that, this is a little bit unfair in this plot. The black points can be shifted up and down by calibration, and these lines have to respect the shape. Right? So that's at most what can be achieved by basically going through these data points. Okay, so this is the first exercise, and since this is very general, then you can go back and look at properties. For example, asking about the consistency of scalar tensor theories, whether that's consistent with the priors. So, for example, do we respect this relation between scalar tensor theories? You most likely change the two gravitational constants with the same signs, and the answer is mostly yes, as you can see here. And we can also gauge, I think this is interesting for many people, we can also gauge after the construction is done, how well, simpler parameterizations would perform. Right? This is the most general exercise that you can do, so you can just look back and ask, for example, if you parameterize these functions as scaling with the time dependence that's proportional to the dark energy density, how that would perform. And the answer is that already at this data level, these simple parameterizations would be almost totally biased and too simple. And this is consistent with the fact that the data is able to express much more constraining power with respect to a couple of parameters. So this part was the phenomenological reconstruction of dark energy properties, where we try to be as vague as possible. And then the second exercise I want to briefly show you is when we try not to be as vague, but we try to restrict to specific families of models where we have a better handle on the physics. So fortunately enough, it was worked out in the past what the most general description of dark energy models when it comes to their, with single scalar field models when it comes to their cosmological phenomenology. And this is called the effective field theory of dark energy, and it basically describes all scalar field models that you can, the single scalar field models that you can have in a cosmological setup. And all it takes is a somewhat complicated geometry exercise, but once you have done, you basically end up with a different set of functions of time that control how your scalar field behave, and perhaps not surprisingly, we end up with a time-dependent cosmological constant. In the standard cosmological model, lambda is constant. Now it isn't the gravitational constant that acquires a time dependence, and then we can go up in covering more complicated models that have non-standard kinetic terms, derivative couplings, and alter the speed of gravitational waves. And the two first functions here control both the expansion rate of the universe and the clustering of structures, while the others only control the clustering of structures. And basically, we can do the same exercise. We can do the same exercise as before, take a theory prior, fit these function of time to the data. Again, all cosmological data that we have available. And the result you see here, and I really like this plot because this is gravitation in our universe, right, as learned from the data. And
may I ask one super quick thing? Do you include the prior speed of GW being close to?
yes, so in the paper there's the whole zoo of models where you change one thing at a time, and the model where you have luminal speed of gravitational wave is there. It turns out that it doesn't really play much into how these solutions work with tensions and other things, or it doesn't really degrade the other constraints. So I like to show the plot where you have everything.
It is left variable.
Yeah, but you can check the paper if you're interested in the other cases.
What are different shades here?
What
are different shades?
Different shades are confidence levels, 1, 2, 3 sigma.
So it seems that this alpha T is not zero at some point, right? At 2 sigma level or something.
Yeah. I mean, we'll see in a second why that happens. But basically, so there's, again, you can read all sorts of interesting results from here. I really like these plots because it's the data telling us something about gravitation, and there's a number of results. For example, the cosmological constant isn't that well constrained. We could live with zero cosmological constant at some sigma, but not too much. Or in some cases the cosmological constant sometimes could have the sign flipped. Now, the most statistically significant feature is this running of the Planck mass that you see here. And we'll see how that ties in with cosmological tensions. On the other hand, the sound speed of the scalar field that seems to be deviating very strongly from GR isn't really doing so because of a data preference, but it's needed. It's the behavior that's needed to stabilize the running of the Planck mass that would otherwise be not physically viable. Right, so that's one of the examples where you enforce physical viability, and then you have to live with this type of results.
Yes, this was another super quick question. Do you remember? Or you surely remember? Can you tell us what is alpha b relative to the speed of sound of the scalar? Is it proportionally? I don't remember. Is it proportional?
It's a complicated relation.
Oh, it's even okay. Okay. And then sorry.
But it basically controls the speed of.
Okay. No, I thought it was a simple one.
But it's not so simple.
Okay. Yeah.
But sorry, you're saying that this plot is in some sort. You're saying that the speed of sound is somehow derived from trying to make sure the other things are physically okay or something like that.
Exactly.
However, none of this is by far the most statistically significant thing. So isn't this a little bit strange? Because the other, it looks like I could live with GR in all of the other panels for the most part, except for here by a big factor. So how is it possible that that thing derives from the others?
So it's basically projection effects. This is a super high dimensional parameter space. So most of the samples there are in that region, but you could relax the stability requirements that you have, and then you would get the same solution without it.
If I fix alpha b to 0, will I get the same mass Planck plot, or it will go all the way up?
But you need to relax stability requirements. So in this case, I'm enforcing that there's no ghost instabilities, no gradient instabilities, that everything is well defined. I would have to get rid of some of those.
Yeah, imagine I satisfy the stability and just put alpha b to 0. Then will I get some large tension with like Newtonian gravity, or no? Will I get?
Oh yeah, in the model where alpha b is 0, you don't get this type of solution. So if you
I will not get any deviation from GR, you're saying.
Exactly, because you can't fit the data better while having a stable model. So that's the problem. That's why this is deviating significantly. There's a whole statistical discussion of how you would see this, but it's basically signal to noise ratio modes again, something like that.
So for stability, like, do you have a prior like correlation matrix that you had earlier?
Yes. So for stability, once you set these functions of time, the code continuously checks whether the input time dependencies are stable or not, and then just rejects the samples that are unstable.
You still have to fit by hand, I guess, some kind of, for like parameters of that prior matrix.
You don't really do it by hand, you do it programmatically, right? So this happens while the fit is happening. But
these are stabilities of the
underlying
scalar
field. Yes.
Gradients
Yes, ghost, gradient, tachyonic instabilities, and so on and so forth. Okay, again, how this plays with cosmological tensions, and not surprisingly, as we saw before, the Hubble constant tension is relieved halfway, while the sigma tension is fully relieved. And you see here, Misha, the difference between the two types of reconstruction. Yellow is scalar, so CT is fixed to 1. That's the tiny deviation from CT equal to 1. It does slightly better on DSA tension, not that much. And you can see that in general it doesn't change much between the two reconstructions. So one of the interesting things is that that the fit is learning is that you remember that in the previous reconstruction we had two different functions doing two different tensions, right? We had the dark energy density as a function of time doing the Hubble constant tension, and we had sigma doing the S8 tension. In this case, the fit realizes that with the Planck mass running, it can do both, or at least both to this extent. So that's I think a nice result. Okay, one of the advantages of working with physical reconstruction rather than phenomenological reconstruction is that you can propagate, once you do this reconstruction, you can propagate all your results back to theory space. And this is, I think, an exercise I've done with Min Supar that you might know because he was an undergrad in Princeton and now he's a grad student in Penn. And I think it really shows the power of physical reconstructions because we focused. We didn't really want to focus too much on tensions. We focused on the simplest dark energy model you can think of, quintessence. And that's specified by a scalar field potential that's in one-to-one correspondence basically with the running of the Planck mass. So we run the reconstruction, and then since we have a physical model, we can just go all the way back to theory space. And I think I'm running a little bit short of time, so I'll be really quick. But the idea is that once you've done this, you can just propagate the entire reconstruction to, see what's the scalar field potential that you have. These are all scalar field potentials that are, perfectly fine with the data that we have. What's the structure of the phase space of dark energy? That was a theoretical instrument that people were using 20 years ago to study, attractor solutions to dark energy. And you can see 20 years of progress in the fact that people were considering these nice swirls, and now the data constrains us to be in this tiny corner. And you can go all the way up to, constrain stream swampland conjectures. For example, there are requirements on the shape of the scalar field potential if it was to come from string theory, for example. And, we just have you've just seen, the entire reconstruction of the scalar field potential. So you can just ask, what happens for these conjectures? Are they satisfied or are they not? And I think this is the biggest advantage of physical reconstructions that really allow you to make statements at a much higher physical level. And in conclusion, I hope I showed you that, we have enough data power to constrain many properties of dark energy at cosmological scales. Enough to make model-independent statements about the stream swampland conjectures that are, something that's very far from data. This was, I think, the first case where we had, data directly talking string theory. That was pretty nice, I think. And these exercises are so general that they are basically observational no-go theorems when it comes to tensions. showing that at late times we can basically relieve the tension over the amplitude of clustering of class-based structures, but just go halfway with the Hubble constant tension. And okay, and constraints are today still at the order of 10% level, which is, once you open up these time dependencies, these are much weaker than what we usually read. And the hope is that, we'll be able to bring this down to 1% with future experiments, as we basically change our perspective from, testing dark energy models one by one to learning them from the data. And thank you.
Thanks a lot, Marco. So, other questions for Marco? Still other questions for him? If not, I have a quick one. The paradigm going from, now I'm messing the words most likely, so was from model testing to model learning. But I thought that all this EFT of dark energy was indeed constructed to give you like the most generic model independent parameterization of dark energy properties, if the only input was that you had one additional degree of freedom.
Mm-hmm.
So then I'm missing something like why not? You worked also on implementing all this EFT CAM. Why wasn't it not enough, like to give already a very model independent as much as possible constraint?
Well,
this is even more in some sense. But...
So in the EFT of inflation, right, all the couplings are you can make some slow roll approximation and then they are constant. In the case of dark energy, they are functions of time.
Yes. Oh, right. So that was.
That's why we have to live with these.
Right.
Things. And why these exercises are so complicated and
yes.
horrendously computationally expensive.
No, I see. I remember them.
Yeah, because you get at the end of the day functions of time, and there's a whole deal of problems in just dealing with it. Right?
Yes. Yeah. I remember. Great. Thanks.
And I think perhaps Matthias said, once, you develop the EFT of dark energy, and then you just go out and measure the couplings. In the inflation case, that's easier.
No, I appreciate. Yes.
Where you have to, cope with
I forgot about the point that you cannot approximate. You're not scaling by and blah, blah, blah. Okay.
If you implement something like solar system priors on these parameters, will there be any room for improvement from cosmology? I guess these models should be. I mean, the models that you described, so scalar tensor models, are very tightly constrained.
So the idea is that at this level, since we are working with linear EFT of dark energy, the idea behind our bet is that the nonlinear part of the theory will get rid of those constraints, because we live in a solar system that's a highly nonlinear region. We live in the galaxy and so on and so forth.
So when you use this like parameterization, like different coupling, different effective gravitational constant for light and matter, it's only on cosmological scales. This is the assumption.
It's usually on cosmological scales. Because it was shown that the nonlinear structure of these theories is very different from the linear. Right? And then at that point, you have to do all the details of how you go from very large scales down to the solar system. So at the end of the day, it's just much easier to work with these frameworks where you don't really know what's the nonlinear completion or the very small scales for cosmological purposes, structures of these theories, and to see what cosmology. But one of the interesting things is that the running of the Planck mass actually starts from zero, right? This was not designed, right? So if we were to measure the gravitational constant on, zero means, what you measure on the Earth is whatever gravitational constant you are measuring in cosmology. That was not by design.
But there are some constraints on the slope as well from some, or not, on the slope of any kind of variation from.
Yes.
local.
Yes. I didn't really. I didn't really take those into. I mean, those are again coming from very small scales, so very small scales observations.
Yeah.
Okay, so I see that some people had to leave because of time, but I think and they only missed the last question. So it was great, and let's thank speakers again, and